So welcome to Lecture 18 in our series on prosody. We'll be looking today at speech recognition and how prosody might be able to help in this process. So the basic idea of the speech recognition or speech-to-text transcription process involves going from a waveform like we have on the left to a word-level transcript like we have on the right. So we can consider the case where our phone recognizer produces an output like this below, and we might realize that that's ambiguous between the pronunciation below and below, and that's a place where prosody might allow us to disambiguate if we have a way of saying that we know that the first syllable is unstressed and the second is stressed. Then that means we have to pick below as our word, and so we can combine phone and prosody information in order to produce the transcription. And that in English may not be as useful as it is in tone languages. It doesn't have as high a functional load, but for languages like Zulu or Mandarin, tone and thus prosodic information have very high functional load and are really important for understanding the language. So that gives rise to a potential strategy for speech recognition to take advantage of prosody. We know that prosody can mark word and syllable identity, and we saw that in Lecture 11. So we can, in some ways, maybe think of prosody as an independent source of information. It's not the same sort of segmental content that's telling us what the individual phones or phonemes are, but instead it carries this additional information. It's also the case that prosody might require different processing. Usually decisions about phone identity in this sort of processing involve short units of spectral information, maybe 25 milliseconds, but the domain of prosody is usually longer than that, so we might need an additional way of dealing with it. Also, prosody might be and can be robust in context where segmental content is impeded. For example, if you're hearing speech in noise or speech from another room, you might not be able to pick out all of the segmental content as clearly, but the prosodic content, maybe the rhythm or the overall pitch contour, might still be quite clear. So let's look at a strategy now for addressing this. So one way we could deal with this is by drilling into this prosody recognition approach. And how can we do that? Well, we can do this using the types of prosodic cues and prosodic features that we've seen in the last few lectures. So we can extract frame level features using things like a pitch tracker. So for example, you get an F0 track, and then you could create some mid-level features by doing aggregation of those features to create, for example, syllable duration information or an average pitch height measure. You could feed those possibly into a classifier and make a decision on whether a syllable is, say, stressed or unstressed. So this sounds really good, but there are some limitations. So if we look at the type of output we might get from a pitch tracker, we might observe that it is not immediately obvious whether a syllable is stressed or unstressed. It doesn't just leap out at you. And also there's a lot of microprosodic perturbation that is an effect of the particular phones being spoken. So if you have a phone like G, it is going to have an effect on the microprosody, and you can correct for that, but you need the syllable identity or the phone identity here, in order to actually make that correction. In addition, if you want to do aggregation over the syllable, that requires having a syllable boundary, which is not intrinsically expressed in the prosody. And in addition, there are a number of higher level contextual features. We saw things like stress shift based on syntax or semantics, as well as tone sandy, which affect the realization of underlying forms in the actual context. And again, all of that may rely on information from phone recognition. So it's hard to get through that path without using phone information. So maybe this sort of bottom-up, low-level prosody recognition approach might not work, but perhaps we can find another way of exploiting prosody. We know that whether or not a syllable is stressed or unstressed has an impact on the realization of its phones. So, for example, you might have a reduced form of a phone in an unstressed syllable. So in giraffe, the first syllable is not stressed, so it might be realized as its underlying phone, or it might be realized as something that's closer to a schwa. And being able to say whether or not that syllable is stressed or unstressed can change the likelihood of a particular phone in context. So we might be able to use this. However, we could quickly end up with the same sort of problem that we observed before, that we need a way of knowing whether a syllable is stressed or unstressed. That again ties into the actual phone recognition or phone identity process, or phone recognition process. So while we can, and we know that prosody does mark word and syllable identity, it is not as simple as our initial hypothesis for incorporating this information suggested. So in many ways, prosody is not as independent of a source of information, at least for this realm, for the level of doing word or syllable identification and word transcription. In fact, prosodic realization is tightly intertwined with the actual segmental realization. And we've also seen computationally that many of the techniques that work for extracting information at the segmental level also provide much of the information that is needed for prosody. And so it is not as either independent or as different in terms of its access as we might have hypothesized. In fact, what we do know is that phonetic and segmental-based speech recognition can be very good even without resorting to explicit prosodic information extraction. And at this sort of unit-linked level, at the level of identifying syllables and words, prosodic information is often quite or relatively redundant with the information you can get from non-prosodic information. And in fact, explicit prosody is not typically used in ASR, even for things like tone languages, because we can get much of that information or enough information for accurate transcription without tone or without prosodic explicit information. There are places where it is used in some models of transcription, for example, for introducing punctuation, where duration changes, silence duration, and also pitch contours can highlight where, say, a comma or a full stop should occur. So what we see is that in most mainstream ASR systems, these models exploit very powerful techniques, for example, those from neural networks, and those systems in turn leverage really large training data sets where tens of thousands of hours of speech and its paired transcriptions, along with even larger quantities of running text, are available, and those together provide sufficient constraint that quite accurate recognition can be performed without recourse to explicit prosodic information. Now, this produces big models, and those sorts of resources are not available for low-resource languages. So there are potential unmet needs where prosody and explicit prosody modeling might, in fact, be useful for speech recognition. So we've seen a particular potential use case for prosody in the context of speech recognition, and in the next lecture, we'll go sort of up a level and take a look at machine learning broadly and how machine learning operates over particular types of prosodic features and how we can find the sort of best prosodic representation for machine learning models. Thank you.